In this video, we will be looking at transformations on a graphed function. In these examples, we will have a picture of a graph, but we will not have the equation for the function. Here we have f of x graphed in blue. What we're going to be looking at is what f of 2 quantity x minus 4 looks like. Now, we know that there's going to be a shift to the right, and we know there's going to be a scaling horizontally, but the question is, what order do they need to be done in? Let's look at two strategies to solve this problem. The first strategy is to look at the function as f of 2 quantity x minus 4 as it was presented in the previous slide. In this instance, the proper way to scale or transform this function would be to shift right 4 and then shrink horizontally by a factor of 2 about the axis of reference. The axis of reference will be defined soon. If we expand the input of this function, or the 2 quantity x minus 4, into 2x minus 8, then our strategy will be to move to the right 8 and then shrink by a factor of 2 about the y-axis. Let's begin by shifting right 4 and shrinking horizontally by a factor of 2 about the axis of reference, i.e. using the form f of 2 quantity x minus 4. Here we see that we will have a shift right portion in red, so we will shift our function to the right by 4. If we shift our function to the right by 4, we have our axis of reference at x equals 4. This is, you can think of as almost the center of the function. It'll be where we do our scaling towards. Since we've moved the function first before scaling, we need to remember to keep this axis of reference as the way that we do our scaling. So since we have a 2 inside our input, it'll be a horizontal scale, and horizontal scaling works kind of the opposite of our intuition, so a 2 will actually shrink our function. So if we have the point 8, negative 1, we need to find its midpoint between our axis of reference, x equals 4. So we can do that very easily by adding the x terms of those points, dividing by 2, and our y component of our ordered pair will stay the same, which gets us to 6, negative 1. If we pick some other points on this graph, we have 5, 2 up there. We need to scale it. We need to find the midpoint between the axis of reference and that point. In doing so, we get 4.5, 2. Picking another point, 1, negative 3. This time we'll be scaling to the right towards our axis of reference. We get 2.5, negative 3. So that point will be right there. Now, if we could imagine doing that for every point along this function, we'd see that our scaling would present a function that looks like this, a graph that looks like this. So this is the result of shifting the right 4 and shrinking horizontally by a factor of 2 about the axis of reference. And we can do this when we have our functions in the form of 2 comma x minus 4 quantity, or in other words, where everything is factored out as much as possible from the input. So now let's look at our second strategy, where we're looking at it as an expanded form where we have 2x minus 8. So here we're going to shift horizontally first by 8 units. So we'll have our red function shift 8 units to the right. Now, we don't have an axis of reference here, but we do scale about the y-axis by a factor of 2. So again, we need to find some points on our shifted function, and we need to find the midpoint between them and the y-axis this time, not the axis of reference. So we do it in the same manner. So 9, 2 will move to 4.5, 2. 12, negative 1. We'll do a short calculation, moves to 6, negative 1. 5, negative 3 makes a move to 2.5, negative 3. And again, we can imagine doing this with every point on our graph, and we get something that looks like this. This should look familiar. This is a function that gets moved to the right 8 and scaled over the y-axis by a factor of 2. And if we bring our function from the previous slide down, we see that they're identical. So both of these strategies work for our graphed functions. Let's do some review. When we have multiple transformations along the same axis, the order matters. If we're dealing with scaling along the x-axis and a shift along the y, the order does not matter. But when we're doing scaling and shifting along the same axis, either x or y, order matters. So, if we have a factored out form of our input, we can move first and then scale about an axis of reference. Don't forget the axis of reference for these problems. If we look at the expanded version, then we can move first and scale about the y-axis. There's no axis of reference if we're going to do it this way. Now, although we didn't do an example of it, the same can be said for vertical scaling and vertical shifting. So if we factor out from our scaling and shifting terms in our function, that means we're going to move vertically first and then scale about an axis of reference. And if we have the expanded version and not the factored version, then we're going to move vertically by b and then scale about the x-axis. There will be no axis of reference.